Alright, so today we're gonna talk about layouts in Cadence. Layouts in Cadence are actually I wouldn't say much easier than Magic, but you don't have to do any commands, you don't have to interact with the command line, it's all graphical. Personally, for layouts, I find that Magic is simpler. But maybe that's because I'm used to it more in layouts than Cadence. But before I start, I just want to remind you of something that we did in schematics last time. It's something that I forgot to mention, and I think some of you made that mistake in the homework. But I didn't deduct any points on it. Was the homework difficult last time? Did it take a long time to finish? Okay, so the issue was let's see, when you have a schematic like this, say I don't know, say your schematic is like this. If it's all symbols like that, it won't work unless you put a VDD and ground just by themselves, like this. So you need to put VDD and ground, like this, just by themselves like that. Otherwise, they wouldn't show up in the global sources, under global sources in the ADE simulator. So make sure you have VDD and ground like that. If you have them already in a schematic, like in a transistor schematic, then you don't need to put them. But there need to be at least one VDD and one ground like that for a circuit to work. That's just something I forgot to mention last time. I'll just go ahead and begin the layout. So let me create a new library. I don't even have to create a new library, but let's just do that again. So here you shouldn't forget to say attach to an existing technology library. Select the first one in CSU, and then you'll have your library. So let me just create an inverter, layout of an inverter. It's the simplest thing, and once we finish, you'll have the homework would involve something just as simple, maybe like a NOR gate or a NAND gate, nothing more complicated than that. So I'll go ahead and create my inverter. So it's remember, you used to put schematic here when we did schematic. Now you just leave it as layout. So layout, and let me call it my inverter. And this is what you see when you're creating the layout. You see two windows. This window here is where you actually draw your layout. This window here is where you select your layers. if you remember in Magic, everything was a box. You did everything in boxes. You did a box, and inside the box you draw something. It's a very similar concept here, except instead of a box you have a rectangle, which is kind of the same thing. But you don't do the rectangle and then you fill it. You actually select the layer and then you do the rectangle. So that's the difference. So remember this, everything is a rectangle. And then with a rectangle you can chop the rectangle in half, you can remove part of it, you can merge the rectangle with other rectangles. You can do a bunch of things. But let's just look at how the basic technique of creating your layout. So you just go to create here, shape, rectangle. So everything is going to be a rectangle. You can create a polygon, sort of like a weird shape if you want, but I've never seen that used anywhere. Probably has some use cases. You can create circles, ellipses, whatever. But all you're gonna need to do is just rectangles. And it's easier, you can see that it has a shortcut key R, so it's just easier to press R instead of selecting rectangle. So remember what's the first thing we draw when doing the layout? Right. So it's the P well and N well. And by the way, here you'll see a layer called DRW and a layer called net, and they're both P well, right? So which one do I choose? I choose the DRW, the drawing. Net, you almost never use the net. I've never had to use it before. I'm not sure what it's used for. So you select PW. For the P well, it's which type of transistor would we be making? PMOS? P well? We're making PMOS, right? With a P well. NMOS, right, yeah. I was waiting for someone to be awake. Okay, so the trick here, I select P well, right? Then I select R, press on R, and then you look at the bottom here. You should always keep an eye on the bottom left corner. It says point at the first corner of the rectangle. So now you know that you're in rectangle mode. So let me draw the rectangle. Before I start, I just wanna, you remember in Magic you had lambda? Here it's the same thing. It's just it's not as clear how much lambda is. By the way, which technology are we working in? It's 45. So lambda would be what? 45 over 2. Except here they actually work on 50 instead of 45. I'm not sure why, but they actually use 50 instead of 45. So here I think each here this still might need fixing here because I'm not sure how much each distance is, but let's say this point here is let me verify something first. Yeah, these need to be modified here. These have to be done by the setup file, but the setup file for some reason doesn't do it, so you have to do it manually. For the major spacing, it should be 0. This is in micrometer, so it's 0.125 and 0.025. So it's 25 nanometer. Is that correct? Okay, so now I've zoomed in. Okay, so between each two dots is 25 nanometer. Okay, so how many dots should I make for my channel? Remember, it was two lambdas. So 2 dots would be the length of my channel here. But let me start again with the P-well. I'm not going to pay much attention to dimensions now. I can optimize it later. So I'll make my P-well. And then I make my N-well. Probably needs to be larger than this anyway. And then I make my channel. It doesn't really matter the order which you go in. Like I said, the channel has to be 2 lambdas like this. Now, to select what do I need for the NMOS? N diffusion or P diffusion? N diffusion, right? So I look for the N plus. That's what I'll use. So I click on N plus, click on R, and I make a diffusion here. And the minimum width for this is the width, right? Now I'm controlling the width. This is the width. So the minimum width here, I don't really remember because the DRC here will remind you of everything. But I think the minimum width is 2 times length of channel, so it's 4 times. Right, so this is 4 lambdas. Okay, let me zoom in. Right, this is 4 lambdas. There's a difference here between this technology and the technology used in Magic. In addition to the N diffusion, we need a layer called active here. So on top of the N diffusion, I need to make a second rectangle called active. This is, yes?
Can we specify the lambda length by type of command instead of we do it by on the layout? I mean, when we draw the width of the gate, can we type the width by command?
You can draw a rectangle by command, but it's more complicated than just doing it by hand. Yeah. In this window here, the main window of Cadence, they have a very, very complicated command language. You can do everything. They have their own programming language, but to learn it, it's kind of complicated. So like I said, we need an active layer above the N diffusion. The same thing goes for the PMOS. So I make a P plus implant. So here instead of 4, it should be what? It should be 8. So this is 4, 5, 6, 7, 8. And then I put an active layer. So this is my active layer. And don't forget to save from time to time, because you never know when the connection might go away. Oops. Yeah, active layer is the same thing for the P diffusion and N diffusion.
What is its function?
Active layer, I'm not exactly sure. I think it specifies that this area is a transistor, but it's not really. I mean, in Magic it's not necessary, but here it's necessary. Anyway, now there's a very useful command called stretch. I wanted to demonstrate it to you. So you can access it by either going to basic, actually oh, there it is, stretch. You can either do edit stretch or just press on S, which is easier. And you can actually do a lot of things with stretch. So as an example, I'm gonna make the N well higher by using the stretch command. So here's what I do. I press on S, and if you read here, it tells select the figure to be stretched. So here I select this area like that, and then I select this point and I stretch it like that. So you can do a lot of things using the stretch command. It's really useful. Another command is the chop command. So say I want to chop this, I press on C, and then I select this. Actually, no, C is copy. Chop is Control C. I'm sorry, I mean Shift C. So if I do Shift C, and then I select this rectangle, and then I make a rectangle like this, it chops it over here. You can undo using U as usual. So now I need to stretch this part here. See, if I put my cursor on just the line, it only highlights the top area. It means that I'm stretching it upwards. So if I select it here, I can stretch it like that. So now I want to put the VDD and ground lines in order to okay. So VDD and ground are just like the other layers. I select metal 1, and then I hit on R, and it needs to be, I think the minimum is 3. We usually do it as 4. We'll do another one here, it's 4. I probably have a lot of DRC errors, but it will tell me about them later, so we can fix them together. The thing is, here there's a web page that lists all the DRC rules, but like you did in Magic, the easiest way is trial and error. Once you build one layout, you actually figure out all the rules because of the errors it flags. So what is left to do here? I need to do the body contacts, right? So for the body contact, remember what layer I used to put underneath metal 1 here for the PMOS? Yeah. So I put N diffusion. So it's N plus implant. And I make another rectangle here. In fact, in addition to that, you actually have to put an active layer. So not only N plus, but also active. And the same here, I put a P plus next to the NMOS and an active layer.
Excuse me?
Yes.
Why do you put N plot into the N1 metal or the PMOS?
Here,
Yeah.
you remember the body contacts?
Yeah. But body contact is P type, right? It's P plot. P diffusion to substrate.
It is?
Yeah. Yeah.
No, it's not. You remember the body contact is the same type as
The well.
the well.
The well, yes.
So what's the well here? The well here is N well because it's a PMOS.
Oh.
I know, I get confused by it too, so. Yeah. Remember, it's always the opposite of the material of the transistor. That's how you can remember it. Alright, and next I put the actual contacts. Now here, for the contacts, this is much easier than magic. Anything below metal 1, anything, you use this layer, contact. From metal 1 upwards, for example, metal 1 to metal 2, you use the vias. So metal 1 to metal 2, you use the via 1 layer. Metal 2 to metal 3, you use the via 2 layer. But anything beneath metal 1, for example, metal 1 to poly, metal 1 to the body contact is this contact, the simple contact layer. So here I put a bunch of contacts. Like this. The same thing here. Okay. I'm pretty sure I have more than 10 errors now, but we can fix them later. So let me put the input and outputs. For example, this is my input. And I need an additional poly here. And then I'll place my contact over here.
Do you need to bring metal one over fully completely, or just side, bring side by side?
What do you mean exactly?
You bring metal one over fully.
Yes.
It's a color. It's actually, is it needed? Is it
Yeah.
essential?
Yeah, there needs to be overlap between poly and metal 1 because the contact does not include the layers. In Magic, the contact already includes the other layers, but here the contact is just the actual contact. You have to place the layers in between. By the way, the good thing here is that if you go to the library and you go to this library here, they have the layouts of all the cells you need. So I can actually verify my layout against the existing library layouts. For instance, this is their layout for the inverter. It's just read only, but you can, if you want to modify it, you have to copy it into another library. But this is their layout for the inverter. Of course, it's much cleaner than my layout. Now you can see that they only place two contacts here. You can see it's not necessary. For instance, what I did here, I extended the metal like this to the border, but it's not necessary. You can just do it like that. This is actually better. I have the habit of doing that, but you don't have to. You just need to put a metal one like that. And the same thing for the output. You don't need to extend it to the border like that here. So they have the layout for pretty much every gate in the library. Okay. So let me just quickly finish the inverter. So here it will be connected. Oops. So this is connected to VDD, this is connected to ground. And this is my output. And finally I have to place the contacts. Oops. This is a contact, it's another contact. I actually need to stretch this. Alright, so let's continue from last time. We had a lot of software issues last time. Now they are all fixed. But when you work on when you want to use layout in Cadence, you have to SSH to swamp 46 to 51, either one, from 46 to 51, because these are the ones where Cadence is working now. Ian's working on fixing the rest of the swamp computers, but right now you have to SSH into these particular computers to work. And when you SSH, by the way, previously you used to use the X flag like this, but you should use the Y flag because the X flag sometimes gives errors and it's not compatible. Use the Y flag instead. And then you put your username like that, and then the swamp computer, say 46. Oh. Okay, so it works. Then go into TCSH. And finally cat setup. I advise you to make a new directory when you want to try the layout, because I updated the setup file and it fixes some issues. So create a new directory for your layout when you want to do it. And then we'll start Cadence like this. Now this is the circuit that we were doing, the inverter. Just so that you remember the steps that we did, when you create a library here, you need to find, sometimes this window goes away and it's hidden, you have to find it, and you have to attach it here to this library, NCSUTech. So this is how you create the library. It wouldn't work unless you do that. I don't need it now, so I'm going to delete it. Alright, so let's resume the layout. And by the way, this layout here has a lot of errors. DRC errors, but we weren't able to verify it last time, so we're gonna do that now. And another thing, the lambda right now is fixed. The issue is the lambda. Remember, we had to fix it manually, but now it's fixed. Whenever you start Cadence, lambda is set at 25 nanometer. So this here, from the small dot, between the small dots, it's 25 nanometer. So the channel length here is 50. I'm gonna go ahead and delete the labels so that we can create them again. Okay, so to create a label, we go here and we create a pin, and then we put them in the order we're gonna place them. So let's say VDD, and then ground, and then in and out. And then we have to display the terminal name and go into the options. For the height, you can put it at, let's say 1 micro, like that. So this would be 0.1 micro, 100 nano. And here you need to choose metal 1 DG. And oh, by the way, you need to select metal here also. So after you did all this, you can hide it and place the layout. The first one was VDD, so you could put it like this. So this is VDD, then it's ground, and in and out. Okay, this should work. Let's save it. And now to verify the design rules, we go into Calibre here and run the RC. Hopefully it will run this time. Okay, it's running. And by the way, this software Calibre is not part of Cadence. This is part of a software suite called Mentor Graphics, which also has Model Sim. So over here, you don't change anything in the rules, you don't change anything in the inputs. In the outputs, basically you don't need to change anything. You just do run the RC from here. It takes a little while, and then it gives you all your errors here. So I have seven errors. I have 2 errors in the active area and 5 errors in the metal 1 area. You can see that this is very different from Magic. In Magic, it will tell you the DRC as you are drawing. It will tell you you've made an error. So in Magic, it's kind of better. Here you have to run the RC every time you want to see if you have errors. So to see the errors, here it will tell you that the minimum well enclosure of active should be 55 nanometer. What this means is that I believe it means that the active the distance between the well border and the active should be 55 nanometer. And by the way, if you double click on the error, it will take you to it here, and we'll highlight it. Here it's highlighted. So what I need to do is I need to stretch the distance here And the same here. And the same thing here. And on the top. So again, to stretch something, you press on S and then you click on the side you want to stretch and you stretch it. Okay, so I'm gonna run the RC again to see if I got rid of the active errors. Okay. Okay, apparently not. Oh, I need to stretch it more than this is just 50. So it needs to be stretched. The distance needs to be minimum 55. So it needs to be stretched one more. Okay. So I'm sure now I got rid of these. Now let's look at the metal errors. So here it tells you that metal 1 must extend past contact by 35 nanometer on two opposite sides. And it's the same for all other errors. Okay. What this means is simply that when you have a contact like that, metal 1 should go past the contact by 2 lambdas. So here I take metal 1. Oh, actually I can just draw a new metal 1 here. Like this. And the same thing here. So the reason it complained is because metal 1 should extend from two opposite sides of a contact. So from this side I should have metal 1, and from this side, and the contact should be in between. This is how contact should always be done. And the same thing here and here. By the way, it doesn't matter if this metal 1 and this metal 1 are different rectangles like that, because they touch each other. It means that they're attached, they're connected. If it bothers you and you want to merge them together, you can actually merge them here. Go into basic, merge, and do that. Now they're the same rectangle, but it doesn't really matter. Alright, let's run the RC again. There's too many windows. Okay, you need to save the design. Still 2 errors. Okay, so these two metals are too close to each other here. So there's a simple solution. You select all this area here and you stretch it. This should do it. And then you stretch this. Oh, and I didn't fix this contact. So what I can do here is I can move this contact, put it here. And then make a polysilicon under the contact again. Okay, this should work. So there's still one more error. Let's see where it is. Spacing here. Oh, these should be connected anyway. Okay, hopefully it will stop complaining. Okay, so it's all right now. And that's it. Finished my inverter. Now, what I need to do is simulate it. But a lot of people, instead of simulating the layout, what they do is that they do something called LVS. Anybody knows what LVS is? Okay, so LVS is layout versus schematic. Layout versus schematic means you make the schematic equivalent of the layout. So if my layout is an adder, I go and make a schematic of an adder because it's much faster to do the schematic. And I simulate the schematic and make sure that it's working. If my schematic is working, then I run LVS, which takes the layout and takes the schematic and compares them together. And if it tells you that your layout is equal to your schematic, and you know that your schematic is working, then you immediately know that your layout is working. So LVS simply compares a layout to the schematic and tells you if they're functionally equivalent, if they do the same thing, if there's the same circuit. And if it tells you that there's the same circuit, and you know that your schematic is working, then you don't have to simulate your layout. Right? Yes?
Can we obtain the layout directly from the schematic or not?
From the schematic? Yes, but you have to go several steps. You have to go into place and route, which is another software that places your gates and connects them together.
So it's the actual compiler doing the job. It's not manual labor work.
To
Once
go
you've got the schematic, you don't have to draw in the layout. Or we have to draw the layout.
if you want to get your layout out of a schematic, you usually get it out of a netlist. For example, if you're gonna do that later in the course, you have a Verilog file. From the Verilog, you get a netlist, a Verilog netlist, and from that Verilog netlist, you can get the layout using the software. But from a transistor schematic here to get the layout, it might be possible, but I've never tried it. It might be possible to get it immediately from schematic, but the way that it's usually done is from Verilog into layout. Yeah. Okay, so let's demonstrate LVS quickly. So I need to compare this layout with what? Schematic of what? Right, so very simple. So I go back into my library manager here, and inside the same cell, I don't create a new cell. Using the same cell, I create a new cell view, and I choose schematic. Okay? Now here, if it asks you about a license, you should always click on always. If you click on no or never, you're gonna have problems. Always click on always. So you can see now, inside my same cell, I have a layout and a schematic view. Okay? Now here, I create my my schematic. Now, by the way, what I created now in the layout are VTL PMOS and VTL NMOS, low threshold devices. If I wanted to create high threshold devices in the layout, I would have to use these layers here, VTH and VTG. VTH is for high threshold. I'm not sure what G stands for. It could be general or something, but VTH or for high. If you don't specify any VT layer, it assumes low threshold voltage, and that's what we'll be doing anyway. So let me put a okay. Oh. So a PMOS and an NMOS, and then I choose my VDD and ground. No, it's an analog. It might work from basic, I'm not sure. Okay. Alright, that's my schematic. So let's make this 180. Oops, running out of battery here. It's not good. Okay. So now I get back into my layout. Let me save this first. And I go into Calibre, run LVS. Okay. And here I choose layout versus netlist. In the layout, I don't change anything. I keep it like that. And you have to make sure that this one is checked, export from layout viewer. So this will extract the netlist of the circuit from the layout, like it used to do in Magic. Then you go into the netlist tab and you specify export from schematic viewer. And these are the only things you need to do. And then you just run LVS. So it's exporting the schematic and the layout to netlists, and now it's comparing them together. So I have two differences. Let's see what they are. The first difference is the width. In the layout, the PMOS width is 200, while in my schematic it's 180, and the NMOS has the same problem. Okay, so I'm just gonna go ahead and change them in the schematic because it's easier. So in the schematic, I'm gonna make the PMOS 200, the NMOS 100. So this was the only difference, the widths of the transistors. All the connections are the same, so that's what matters. So let's make it 200 here, and $100 here. Save it and then run LVS again. Is it finished? There seems to be an error somewhere. Alright, so I just needed to save it. And I got the smiley face. When you get the smiley face, you know that there's the same. So everything matches. If you want to see the comparison here, it compares everything. It compares the pin names, input, output, compares the netlist, connections, compares everything. So that's how you know that it's working. You can see the slightest difference, it will detect it. So that's how you know that if your schematic is working for sure, you don't need to simulate your layout. You just need to make sure that they're equivalent through LVS. If you still want to simulate your schematic, your layout, let me see if I can do it. I have 10 minutes of battery. What you need to do is you need to run PEX. Now in PEX you choose to export your netlist. So you choose to export your netlist from schematic viewer, and you see like this. So you need to have the schematic. If you don't have the schematic, then you need to choose. Remember when we run LVS here, we had this the layout netlist here, so you choose this file. Otherwise you would choose export from schematic, and that's it, all you need to do. And after you're done, it will generate a parasitics file. It will generate a bunch of spice files, one for resistance parasitics, one for capacitance, one for inductive parasitics. We can take a quick look at them now. And after that you have to use HSpice like you used to use in Magic to simulate everything. But this is not required from you in this course. In this course you just LVS, that's all you need to do. My laptop's gonna hibernate soon. Don't be surprised if that happens. So this is my main netlist, and this is a parasitics that it generated, and this is another parasitics that it generated, and you can simulate that in HSpice later. Anyway, that's it for today.